So let's now finalize our guidelines for the three classes of data types that we're going to be using in Go. We've already set the guidelines for the built-in types, right? We said that we're going to be using value semantics to move that data around our program. If it's a numeric, a string, or a bool, I don't want to see you taking the address of these data types, right? The only time I'll be okay with a pointer of type int, string, or bool would be a field in a struct where we have to represent the idea of null, which happens on occasion with our certain relational databases. But other than the idea of null, right, that would be the one exception. Unless you had something else that was truly reasonable or practical, I don't want to see it. And remember, also with the built-in types, when we're moving that data around using our value semantics, all that mutation, all that reading and writing is also being done with that value semantic. In other words, it's all done in isolation. Now, I did tell you that the second class of types, the reference types, we also should be using our value semantics to move that data around our program. Everybody gets their own copy of the slice, the interface, the channel, the map, that function. They all get their own copy of it, right? We're trying to minimize pollution on the heap. The thing is that when you're reading and writing with that reference type, you are in pointer semantic mode. You got to remember that, right? That's the duality of that type. I want to show you a little bit more around those reference types here to solidify this a little bit more. And I want you to take a look at these two types right here on line 20 and 21. These are types that are defined in the net package in the standard library. Now, again, these are custom types, and they're custom name types, IP and IP mask. But what I would say here is that they are based on an existing data structure, in this case the slice. So since IP is based on a slice of bytes, that's the internal data structure for an IP address, IP mask is also based on a slice of bytes. They're technically now reference types, aren't they? I mean, if it's base data structure is a slice, it makes them a reference type. And if they're a reference type, what does that mean? It means that we're using our value semantics to move them around our program, but they have that duality where we're using our pointer semantics to read and write. Now I want you to take a look at this method here on line 26. This method is called mask. Now if you look at this, this is really a mutation API, but notice that it is a value semantic mutation API. One of the things that I want to drive home here is that we should never really be confused about how to design an API once we know what the data or the input is, once we know what the output is. Because the data itself is defining how it comes in and out of these functions. And so if we were to use pointer semantics here for mask, right, you would be using the wrong semantic because slices don't use pointer semantics, they use value semantics. So that's why we're seeing a value receiver and we're seeing the return. This is, again, just like append, a value semantic mutation API. Really cool stuff here. And regardless, right, here is a function. What does this function take on line 47? It takes a value of IP. What does it return? A value of type string. Why? Because these are data types that use those value semantics. Like I told you before, I could take a look at your entire code base and almost on data semantics alone let you know how much trouble this code base is in or not. We could find bugs just by looking for inconsistencies in the data semantics. And this is all driven throughout the standard library as well. Now, I did tell you that there are exceptions to everything, right? There really are no absolutes. And one of the exceptions around these reference types fall within the category of both slices and maps. There may be a time when you need to take the address of a slice or the address of a map, but normally the guideline is you'll do that if you're sharing it down the call stack and into functions that are either called decode or unmarshal. So remember that. Decoding and unmarshaling require pointer semantics. They're just the nature of the activity. So if I'm doing a code review and I see you take the address of a map or the address of a slice, as long as it's being passed down into functions like decode or unmarshal, that's reasonable and practical. I won't say anything. Other than that, probably the code review will stop and we're going to want to look at what we're doing, right? It doesn't mean that you don't have a good reason, right? There are exceptions to everything, but it's something that we're going to want to check. Now, let's take a look at our struct types, because we haven't really talked about the struct types. I talked a little bit in the last section about that user type, and I suggested that it should be using pointer semantics because we can't make copies of people in the real world. And here's another struct type that comes from the time package. It's called time. You can see that it's a fairly small struct, right? A 8-byte and a 4-byte integer and a pointer. But sometimes it's obvious that something should be using a value or pointer semantics. Sometimes it's not. And here's a question that you can ask yourself. It doesn't always apply, but sometimes it does, and it's a good indication of what we should be doing. Again, we're not making decisions based on performance. We're not making decisions based on the idea that something could or could not be copied. We're doing it based on correctness. What is the reasonable thing to do for this type of data? What is the expectation? What are people going to assume when they look at data like this? Now, one question you can ask yourself, and we can look at time, is this. If I have a value of type time, here it is. Here's my value of type time, and it represents 5 p.m. Right? And I add 5 minutes to it. Is it the same time value, just 5 minutes later, or does 5:05 represent a different piece of data? This is something that we can ask ourselves. When mutation occurs to the data, is it the same piece of data modified, or is it a brand new piece of data? Now, when it comes to time, I like to think that 5 o'clock and 5:05 are two distinct pieces of data. And with that idea in mind, value semantics tends to make more sense. Just the same thing that we saw with the string. If you have a string and you modify or mutate that string, you get a new string. And we go back to the user value for a second. I mean, think about that, okay? If I have a user value, let's say that the current user's name is Jane, and I turn around and I decide that, we're going to change Jane's name to Sally. Okay? Does that change who Jane is? I mean, even you, who I'm looking at right now, if I change your name, does it change who you are? No, it doesn't change who you are. It's just a small modification that I've made to your name. You are still who you are. When we have data that doesn't really change based on a modification, then usually pointer semantics are the correct way to go. And if you're not 100% sure what semantic to use, we always use the pointer semantics, even though it's a little bit more dangerous to work with in terms of our mutation, only because you can't assume that all data can be copied. As an example, if you add a mutex or a wait group, when we get into multi-threaded software development, if you have fields of these types, then that data is no longer able to be copied, right? So when you're not sure, the safest way to go is your pointer semantics, sharing it. And remember, the cost of pointer semantics is we have to be extra careful when reading and writing. So let's take a look at what the language team chose to do with this struct type here. And the best way to know what semantic is at play is to just look at the factory functions. And when I'm doing a code review, what I want to see is the type, factory functions next, and then methods, always together. Don't scatter your methods throughout a code base across multiple files. Keep these things together. And another thing is you don't need a separate file for every type. You could easily put 500 or more lines of code in one file if you organize things correctly. And part of your readability reviews and your mental models of a code base should be, is this code file readable? Are the things that I'm going to be touching the most maybe at the top? Does everything kind of present itself in a logical order? Do that as part of your readability review. Now, this factory function is called now. It comes in the time package, and I want you to look at the return. The return type tells us a lot about the data semantic that the developer chose. And you can see here that this function returns a value of type time, a value of type time. So what this is saying is that value semantics are at play. It means that any function that accepts a time value should be done by value, returns time should be done by value, a field in a struct should be done by value. Again, what would be an exception? Needing to represent null could be an exception. Again, unmarshalling or decoding could be an exception here. But as the general guideline, the developer's telling us value semantics for time, which is fantastic because if we're just moving time values around by themselves, we can pretty much guarantee that we won't be polluting our heap. Now, let's look at a method here called add. Add is a mutation operation. A lot of Go developers early on might have chosen pointer semantics because it's a mutation. But what does this API do? It uses that value semantic mutation API. Why? Because time has to use value semantics. Again, the API must respect the data, not the other way around. I'm taking huge cognitive load off your back. There is no more guessing how to design an API as it relates to the data. We have to know what the data is. We have to know what the data is defining in terms of semantic, and then we can design the API to provide that functionality that it needs to provide. So in this case, we've got that value receiver there on line 77, and it returns a new time value, just like append. Okay, just like that mask function that we saw before, value semantic mutation. And again, it even goes all the way through functions. Divide is taking a value of type time, value of type duration, which is based on an int64, returns an int, returns a duration. I haven't shown you one pointer yet, have I? No, not at all. Because this is all data so far that leverages that value semantic. Now I told you again, there's one exception. There are times where you might need to go from value semantics to pointer semantics. There can be exceptions. Normally, if we're going to move from value to pointer, which is changing semantic, it's going to be done in a very small scope and normally around ideas of decoding and unmarshalling. And I want you to look at these 4 methods that are part of the standard library here on line 101 through 105. And what you can see here is that the API has now switched and defined these methods with pointer semantics. But look at the name. What are the names of these methods? Unmarshal and decode. They're helping to define interfaces that are out there. These are operations that require. So here's that exception where we're going from value to pointer semantics, okay? And in a small level of isolation. And I told you that there are no absolutes, but I do have 2 absolutes in this class. And the very first one I'm going to share with you is right now. And for me, this is an absolute. It is okay to go from value to pointer semantics in a very small scope like this particular method. But it is never okay to go from pointer semantics to value semantics. We are never allowed to make a copy of a value that a pointer is pointing to. If a value is shared with you, you can't make a copy of it. I don't care if you think you know it's safe. I don't care if you know it's safe. It's not safe. The whole idea of saying that this is using pointer semantics means that there's only ever one, and it's always being shared. You start mixing a semantic from pointer to value, you are going to have problems. Maybe not today, maybe not tomorrow, but you will. And unfortunately for me, that is an absolute. Code review is going to stop. I'm going to be digging my feet in the sand. I'm not going to allow it under any circumstances. All right, so remember, from value to pointer in small situations, yes. From pointer to value, never, ever, never. Now, let's take a look at this factory function here. This one is called open. Notice it takes a value of type string. Again, string uses the value semantics. But what is this function returning? A pointer of type file. Here is a factory function using pointer semantics. Again, we're going to look at these factory functions to help us identify what the semantic should be or what it's in play. And in this case, what the OS package is saying is that we share file values. Regardless of the operation, they must always be shared. And if we look at more of the API, here is a method named change directory. Look at this method. This method's using pointer semantics on the receiver. Why? Because we must be sharing file values. Even if the method doesn't mutate anything, it must be shared. It's not safe anymore to make copies of those file values. And again, that goes all the way through even functions. There's a pointer of type file. We're sharing it. Now, error is an interface. That's a reference type. So we're using our value semantics. Pretty cool. So let's just recap our guidelines right now one more time, because we're going to see this consistency now throughout our code base. These are consistencies you're going to see throughout the standard library, and these are things that you really want to focus on a micro level. It's going to make your code base really solid. It's going to make your team solid. So, built-in types. We use our value semantics to move that data around our program. We use our value semantics as fields in a struct. And when we're reading and writing, we're also in that mutated isolation. Reference types. We're going to be using those value semantics to move it around our program. We're going to move that slice. Everybody gets their own copy of the slice, the interface. But when we're reading and writing, we're using those pointer semantics. That's the shared access on reading and writing, right? And there's the exception of being able to take the address of a slice or a map when we're sharing down a call stack into functions like decode and unmarshal. And then when it comes to our struct types, we have to make the decision. That's that third class of types. At the time you define the type, you have to decide, am I using pointer semantics or value semantics, and maintain strict consistency with this. And if you make a mistake, change it, refactor it, fix it. Remember, we're not going to have that cascading code effect because methods don't care whether you're using that address or the value. The method can adjust on the call. It's beautiful. So you can make those changes. But once you set that, you stick with it unless you feel like you've made that mistake, right? And again, we can go from value to pointer semantics in small places, but never pointer to value. That's an absolute no-no. Massive integrity. So we now have our guidelines in place for the three classes of types. And we're going to be leveraging these guidelines moving forward. You might still see some mixing of semantics as we continue to learn mechanics, but once we get into design, we won't see any more of that. And this is something that you could go through and fix in your code pretty early on, and it's really going to help you, your team, and your products.